Okay, we're at the last part of chapter 3 where we get to learn how to quantify how many eggs we need or how much cookies we can make, okay? And so I'm going to use this example, which is partially derived from our experiment 4 in lab, but you should know this is not the complete reaction. In order to do this properly, you actually need all of the 4 steps to be added together. I'm just using the first step as an example. Okay, so don't copy what I do exactly, but think about how you can apply it to the experiment. Okay, so and also, by the way, you're going to start with way less than 5 grams. This is a lot of aluminum. It would take a long time to dissolve. All right, so here's our strategy in order to figure out how much of a product is made. It would also apply if you needed to know how much of another reactant gets used. So you can actually make ratios out of any component in a chemical reaction. All right, the first thing we need to do is make sure that the equation is balanced. So we already went over that. You should pause the video and try to do that really quick. Okay, so that one probably took you a few minutes. It took me a few minutes, even though I kind of know what to look for. That happens because the oxygen and hydrogens are occurring in so many of the different pieces of this reaction. Okay, so the key for me was realizing I have 4 oxygens on the right-hand side minimum. And so no matter what, I have to multiply, I have to have an even number. No matter what I multiply 4 by, it's going to be even. So I had to double the KOH, which means then I had to double the KAlOH4. And then I had to double the aluminum. And once I do that, if I focus on balancing the oxygen and worry about the hydrogen later, because it's all by itself right here, so that makes that one easier to handle. So then you end up with the 2 oxygen from here, plus some number of oxygen, and it has to add up to the total over here, which is 8. So I put in a 6. And that's how you get to 8. And so we need to have a 6 on this oxygen molecule here, this water. Then I worry about the hydrogen. So it was 12 from the water and the 2 more from the KOH, and that's how I got to 14. And then I said, okay, well, I got 8 in the KAlOH4, and how many more hydrogen do I need to get to 14? I need 6. So then I have to put a coefficient of 3 there. That's only step 1. Okay, so these problems are a little time consuming, but they teach you a lot of really important concepts. All right, so now we've got a balanced reaction, and the next thing is to go from grams of aluminum, so we're going to go 5.0 grams of aluminum, into moles. So this uses the molecular weight. So we have to look at the periodic table and find out how much aluminum is. 26.98. And a lot of the time people will do this. They will say, oh, it's 26.98 grams per mole, and then suddenly realize that nothing cancels. This is the point of writing units on everything you do. I know people are trying not to, but it won't work because then you're going to do your math upside down. So if you're struggling to get the right answers in ALEX or on our Kahoots and all that stuff, make sure you're just writing the units. It's a really important key piece, right? Because then I know I have to go 5 divided by 26.98 instead of 5 times. So we get 0.185. I am keeping 1 extra digit even though I only have 2 significant figures because I don't round until the end. So that's how much aluminum we have. Then I'm going to use what's called the stoichiometric equivalence. Stoichiometry is the relationship between different amounts of different substances in a chemical reaction. It's a German word, super fun, hard to spell. But really this whole chapter is about stoichiometry, okay? Not stoichiometry, okay, whatever. It can't caption that correctly. Anyway, this is how you spell stoichiometric. And stoichiometry is the same thing, but with a Y at the end. All right. This is also more easily pronounced if you call it mole ratios. And so mole ratios come from the chemical equation. So I'm going to clean this up just real quick and get my balancing out of our way. So the coefficients in front of the numbers are what you're going to... I was trying to erase the I. That was funny. Did you see that? So the mole ratio always comes from having a balanced chemical reaction. So in this case, I want to put, it's still dimensional analysis, so we're setting that up right away. I want to put what I'm starting with on the bottom, so that would be aluminum, and what I'm trying to get to on the bottom, on the top, in this case we're trying to get to the KALOH4 product. So before I even start worrying about numbers, I try to fill in what the units are that I'm trying to get rid of on the bottom and what I'm trying to get to on the top. And then I go back to the chemical equation and I look at the coefficients. So there's 2 aluminum and 2 of my product. That's where the numbers come from, balanced reaction. Okay, so the molar ratio always comes from the coefficients of a balanced reaction. I've said it like 5 times. I hope you wrote it down because you're going to forget, but that's a very important thing. Now, mathematically, we're not changing anything here because this is just like multiplying by 1. But in terms of the unit, we have a big change. Now we're talking about product instead of reactant. And then the very last step to figure out, when they ask us how much, that usually means grams. So our last step is that we need to find the molar mass of this in order to go from moles to grams. So I calculated 134.12 grams per mole for this compound. And so all we'll do is take the moles we have, just like we were practicing before, and multiply so that you get to the grams you want, and you cancel moles. So our final answer to the question is that from 5 grams of aluminum, we get to make 24.8122 grams. I only have 2 sig figs, 5.0, so we're just going to round that up to 25 grams. Okay, so this is an example of molar mass conversions. Really, really key idea here. So if you're at all confused, do a few practice problems, watch the video, take notes, all of that. And then move on to this topic, okay? Because your understanding of this, of the molar ratio uses, is critical in understanding this concept, limiting reagents, okay? So, I have an Xbox 360. We're almost 2 generations past that now, but that's what I have in my picture. And I want to have a party with my friends, and of course the 360 has 4 controllers that we can use. So 7 people come over, and I only have 4 controllers. Okay? How many people would stay at my party? Let's assume I didn't buy beer or pizza. Of course, it's just the Xbox, that's all. Of course the answer is that 4 people can play, so 4 people stay. And so the question is, what do we run out of first? Because that's what limits the fun of the party. That's what we would call a limiting reagent or a limiting reactant. Reactant and reagent are synonyms. In this case, the limiting reagent would be the Xbox controllers. If I had 8 Xbox controllers, everybody could have stayed, and the limiting reagent would have been the number of friends I have. That's probably more true than this example. I have a lot of Xbox controllers. Okay, so let's do a real chemical example here of a limiting reagent problem. So what the question we're trying to answer here is, how much product can we actually make? In these kind of problems, they're going to give you an amount of all your reactants, and you have to calculate how much product can be made from each reactant. Whichever amount is smaller is the answer. You can't make more than your limiting amount, right? You can't have more than 4 people play Xbox because you have 4 controllers. All right, so let's walk through this. If we have 10 moles of H2 and we have 7 moles of O2, Which one do you think is going to be limiting? Are we going to run out of oxygen first, or are we going to run out of hydrogen first? Well, let's figure it out, right? So this is just another chance to use mole ratios. So if we start with hydrogen, we have 10 moles of that, and I'm going to convert it into our product. So 2 hydrogen go on the bottom, and 2 water go on the top. So if I have 10 moles of hydrogen, I can make 10 moles of water. Okay, this is a 2-to-2 ratio. I didn't actually pick up my calculator because I know that's going to be a 1 and it doesn't change anything. But again, it's important to show our thoughts clearly by showing our math so the units cancel. Like that. Ooh, Christmas colors. It's too soon. It's not even Halloween yet. All right, so let's do the same thing for our 7 moles of oxygen. This ratio is going to have 1 oxygen for every 2 waters. And so if I have 7 moles of oxygen, I could actually make 7 times 2, which is 14 moles of water. So now we want to look at this and we want to figure out which one is actually true. And in this case, the hydrogen is what we run out of first. So that means our limiting reagent is hydrogen. Even though we have a higher number of moles, the reason for that is the ratios are different. All right? So if I have 7 moles of oxygen, I can make 14 moles of water as long as I have enough hydrogen, but I don't. I run out of hydrogen. And so if we want to figure out how much we actually make, okay, you can actually only produce 10 moles of water. So let's figure out how much of our oxygen has to react to do that. Five moles. Okay, so we started with 7, we reacted 5, so 2 moles remain. This is what we call the excess reagent, okay, the one that's extra. So in our final mixture, I will have 10 moles of water, no moles of hydrogen, because it was limiting, we used it all up, and we will have 5 moles of oxygen that has reacted to form water, 2 moles of oxygen that will remain. So we end up with 10 moles water and 2 moles of oxygen. That's what's left at the end. Okay, so our limiting reagent is the thing that isn't present at the end. That would be our hydrogen. Okay, so it takes a little practice. It's easy when I show you, but it's harder when you're trying to apply it in problems by yourself. I usually make an analogy. Let's say Professor Miller starts a daycare. This is a terrible idea, but let's say that I do. But I forgot to go grocery shopping, so all I have is 3 pieces of cheese and let's say 9 pieces of bread. So how many of the children in the daycare can I feed if a cheese sandwich, well, there's 2 E's in cheese, if a cheese sandwich is 2 bread and 1 cheese, right? Well, if it's based on the bread, we would go 1 sandwich for 2 breads. We can make 4.5 sandwiches. If it's based on the cheese, we can make 3 sandwiches. Only one of these can be true, right? What is going to happen is I'll be able to make 3 sandwiches and I will have some bread left over, right? I'll have 3 pieces of bread left over, okay? Sometimes books will use bicycle tires and bicycle frames, but it's all the same kind of idea. And going back to the cookie thing, eggs was my limiting reactant because I didn't have as many as I needed, and I was assuming I have the rest of my ingredients, right? And so eggs are limiting how many cookies we can make. Okay, so once we know the limiting reactant, you can figure out how much product can be made. So in our water example, I skipped a few slides, by the way. So a theoretical yield is based on the number of moles of product you can form based on the limiting reagent. So here I figured 180.2 grams of water. If I actually do my experiment and I only weighed out say 95 grams of water, that's my actual yield, that's measured from the lab, then I can figure out how accurate, how good my yield is by simply taking the 95 grams and dividing by the theoretical yield, so what I thought I was going to get. And the bigger this percentage is, the better off you did. Okay, the less transfer loss you had, the less, the more product you formed. So in this example, we didn't do too great. It's 52.72%. That's like getting a 52% on a test. We had a lot of transfer loss. We had a lot of spilling, or our reactions did not go all the way to the end. You might also have more than 100%. That means you have contamination, usually from water.